Great, thanks. All right, so memory, CPU, network. These are generally the three components of a computer that we need to use, and we need to use efficiently. Most, one would argue, numerical relativity codes indeed prioritize these, as we need to first focus on network so that we can get excellent scalability, followed by, well, CPU and memory. And well, if you're scaling to a bajillion nodes, then maybe memory isn't even that important. What if I told you that it's possible to perform binary black hole simulations, mind you, state-of-the-art binary black hole simulations on a consumer-grade desktop? Well, it requires a reimagining of what we mean by next generation. Basically, we have to reprioritize. First priority is memory, because we're very memory constrained on a consumer-grade desktop. Second, CPU, because, well, we don't have that super high-end CPU that we can generally expect. And finally, yeah, we want to get to the network bits, but that'll be post BlackHoles at Home launch. So BlackHoles at Home is a proposed volunteer computing / citizen science project in which we wish to fit full numerical relativity binary black hole simulations, like I said, on consumer-grade desktops, and utilize that capability to generate large-scale gravitational wave follow-ups and catalogs. And it's also the name, conveniently, of the code behind the volunteer computing project. It's a NURPy-based code. And NURPy Plus itself builds on the numerical relativity and spherical coordinates work pioneered about a decade ago, but extends it to a much broader class of spherical-like, cylindrical-like, Cartesian-like coordinate systems to create, with the help of BlackHoles at Home and the infrastructure therein, the ability to solve Einstein's equations on grids that look like this. Really, I would argue BlackHoles at Home is why I originally decided to start writing NURPy Plus. Why use it? Well, this grid structure is ridiculously efficient. Like, we're talking, for every Cartesian AMR, for every grid point we used here, we need at least 100 Cartesian AMR grid points. So this is what enables binaries black holes on the desktop, and we'll see it's also super accurate, surprisingly enough. So here is the result from the Einstein Toolkit Gallery example, the GW150914. After about 5 orbits, looking at the orbital plane after about 5, like I said, after about 5 orbits, this uses about 203 gigabytes of memory. And this, like I said, GW150914, so it's not an equal mass system. Both black holes have some spin. And again, it's using Cartesian AMR. Using BlackHoles at Home like grids, notice that the numerical errors are actually smaller almost everywhere, despite the fact we're using less than 1/100th the number of grid points, 1/100th, I should say, the amount of memory. Looking at the payload from this simulation, the gravitational wave, we look at the dominant mode and we see excellent agreement between the Einstein Toolkit and BlackHoles at Home. However, when we look at these higher order modes, these modes that may be very important for next generation gravitational wave interferometers, we start to see noise appearing in the Cartesian AMR-based run, the trusted code. And this noise has been understood now for more than a decade. In fact, I studied it some years ago. And it has to do with the fact that there's a sharp gauge feature that propagates out from the initial data and is partially reflected. As we go out in a Cartesian AMR grid, our resolution drops by these discontinuous factors of 2. Eventually, that sharp gauge feature can no longer propagate through one of these boundaries and is partially reflected, resulting in a very slow to converge source of numerical noise that also impacts, as you can see, the physical signal. Even though it originates as gauge, of course, in Einstein's equations, gauge and physical space-time quantities are coupled. We also compare against, and I downloaded an old SXS waveform. Jeffrey was telling us some of the history of this. So this was the very first catalog. I chose a shorter waveform to compare against, circa 2013 version of specs. Notice again, you see excellent agreement in the dominant mode. This is a Q=6 example. So this is a 6-to-1 mass ratio performed on desktop level resources. Then when we go to higher order modes, we notice that BlackHoles at Home even has a little bit less noise than spec, at least this old version of spec. And I'm actively collaborating with the folks in the SXS collaboration, trying to figure out what's going on with this particular waveform. So you'll notice in these previous slides that I'm not showing the merger. Well, the reason is we couldn't do merger, and these results are about 12 months old. We can now do mergers, and the reason for that is I completely rewrote the code. So basically, the idea is I sort of have. You can see that there are like different coordinate systems inside other types of coordinate systems in these numerical grids. And what I've done is I've developed this sort of Lego building blocks approach to where before it took to generate a new grid structure months, now it takes a matter of minutes doing it this way. And I have to brag that we now have an Einstein Toolkit interface, which makes use of the state-of-the-art apparent horizon finder within the toolkit, H-Finder Direct, so we can get full binary black hole or full single black hole diagnostics, including spin and apparent horizon information. So what I want you to do is take a look at this left panel of this movie, which shows the grid structure over time. It's going to show you how the grid structure changes very rapidly near merger. Now, you might be worried that the numerical errors might spike close to merger, which is common in numerical relativity codes, that the numerical errors actually don't behave very well as you get close to merger. So we're next going to look at the log base 10 of the absolute value of the Hamiltonian constraint, which is on the right here, and watch what happens near merger to the constraint value. So the dark would be below constraint value, which is the lower numerical error. It actually drops, which I'm very proud to say. We look at the gravitational waveform from this particular simulation, and we see that, again, with the latest version of the BlackHoles Home, with the rewritten version, we still see this beautiful, very low noise level in our gravitational waves extracted all the way to L equals M equals 8, and decades of beautiful ring down after mergers.
2 minutes.
So what I'm going to apply here on the left is the log base 10 of the Hamiltonian constraint violation along the white line pictured on the right. And this is a convergence study performed using this unequal mass scenario with both black holes are spinning after about 3 orbits. And you can see when I flip between the fiducial resolution and 1.25 times higher resolution that the numerical errors seem to converge pretty uniformly throughout the grid. And in fact, when we measure that, we see that it's about 7th order convergent, which is consistent with the interpolation order between these numerical grids. Kind of as expected. So the code has been rewritten over the past 12 months to handle mergers. The extractor gravitational laser constraint looks awesome. We hope to be launching BlackHoles Home when it's ready. And that basically there's a to-do list right there. We're going to fix the most important bugs. There's currently a crash having to do with our outer boundary condition.
1 minute, please conclude.
Of course. We're going to be next releasing the paper and the code. And then the Boink server client will be launched shortly thereafter is the plan. And we received funding to Charm++ parallelize this code base. So finally, that third item on our priority list will sort of raise up on the priority list. We're going to add Illinois duration support for next generation binary neutron star and binary black hole simulation. So thank you very much.
Do we have questions for that? We have.
Oh, yeah, Jeffrey.
I have a question and a comment. The comment is you're using Charm++.
Oh, thank you.
And the question, this is curiosity. Have you looked at the jump radiation in BlackHoles Home? Is it noticeably different or better?
You know, I found the jump radiation in all 3 codes. Yeah, sorry. The question was, is the jump radiation comparable, or how does it compare between Einstein Toolkit, BlackHoles Home, and SPEC? The fact is, it's like the order of magnitude is just right on top of each other. The initial data, in other words, has similar levels of jump radiation. So great question. Yeah.
I guess along that line, it's using like nearby initial data or.
Oh, it's actually using 2 punctures initial data. Yeah, we hope to move to NERPI elliptic soon for our initial data for binary black holes. Yeah, Matt, sorry.
So should the people who are using Einstein Toolkit, box-in-box Cartesian grid switch, is there still any advantage in the old method?
I think the old method, at least, look, BlackHoles Home is designed for black hole binaries, and therefore all the grids have been tuned accordingly. I think Cartesian AMR generally, especially talking about CarpetX, is always going to be best for, you know, that general purpose simulation that you want to perform where there's not necessarily any particular symmetries involved. I think you're going to get a quicker turnaround there. Although I think if we program this gridding structure appropriately well enough, then you know you might be competitive there. I don't have a lot of features that CarpetX actually already has, like hydrodynamics and GPU support. No symmetries.
Okay, yes.
Yeah, none. But I mean, sort of near symmetries, right? That's the motivation for using spherical chords. You don't need to sample as much in the angular directions as the radium. Yeah, sorry.
Have you looked at momentum constraint violation?
I have looked at momentum constraint violation, yes. So momentum constraint violation is a little bit lower order than the Hamiltonian constraint violation, something like 6th order. Keep in mind, I have time stepping of it's actually 3rd order. Then I have my spatial finite difference is 8th order, and my integral interpolation 7th order. So it has to be somewhere between sort of 3rd and 8th order. So yeah, momentum constraint is not terrible. 6th order is better, I think, than what you'll get from Cartesian AMR, but I'm going to look into ways of improving that.